Everybody to the our seminar. It's my great pleasure to introduce Professor Volodymyr Mazorchuk from Uppsala University. He will speak on homological invariants of category O. Go ahead, please.
Thank you very much. Thanks a lot for the invitation and for giving me an opportunity to give a talk at this seminar. I will now switch to the full screen mode, so I will not be able to see anything else but the presentation. So I have organized this talk in the colloquium style talk. I will tell the story about some homological properties of category O and some results related to this. And I will start with the definition of the main object. So what is category O? So category O is a certain category of modules over a simple finite dimensional Lie algebra. So we fix a simple finite dimensional Lie algebra over the field of complex numbers, and we fix a triangular decomposition of this algebra. So for example, what all this means, so for example, we can take as the algebra itself, the algebra SLN of all n times n matrices with trace 0 with respect to the usual commutator of matrices. And then the middle part of the triangular decomposition, this is a Cartan subalgebra. That's the subalgebra of all diagonal matrices. And then n plus is the subalgebra of all upper triangular matrices, and n minus the subalgebra of all lower triangular matrices. So the abstract setup is a generalization of this kind of things. We take all matrices and split them into the strictly upper triangular, diagonal, and strictly lower triangular. Let U of G be the universal enveloping algebra of G. So a Lie algebra is not an associative object. So if we consider representations of Lie algebras, this problem is equivalent to the problem of representations of some associative object, which is called the universal enveloping algebra. So this is an associative algebra, and the representation theory of the non-associative object G is exactly the same as the representation theory of this associative algebra U of G. The problem is that we start from something which was finite dimensional, but the corresponding associative object is usually infinite dimensional. So the representation theory of infinite dimensional algebras is much more complicated than that of finite dimensional algebras. And the claim that it has the same representation theory, there is a canonical isomorphism of categories between the category of all modules over the associative algebra U of G and the Lie algebra G. So they are the same. And now I want to define category O. So category O is a very, very tiny subcategory of the category of all U of G modules. And how to get this category, the general philosophical principle behind the definition. So if you have a big infinite dimensional algebra, then quite often, in order to get a reasonable category of modules, you have to kill 1/2 of the parameters of your algebra. And so we have, our algebra is now divided into 3 parts, n minus h and n plus, and we have to put some conditions on 1/2 of these ingredients. So what are the conditions? So here is a definition. The definition is due to Joseph Bernstein, Israel Gelfand, and Sergei Gelfand from 1975. So category O is defined as the full subcategory of the category of all finitely generated G modules, which consists of all G modules with the following 2 restrictions. First of all, the Cartan subalgebra H, it acts diagonalizably on the module, so there is an eigenbasis for that action. And the algebra n plus acts locally nilpotently. So basically, we have the commutative Cartan subalgebra, and we want the commutative, this commutative subalgebra to act diagonalizably with an eigenbasis, and n plus, we more or less say that the unique eigenvalue which we allow for n plus is 0, and so everything should act locally nilpotently. Okay, so here are the basic properties of category O. O is an abelian category, and each object of this category has finite length. So this is a kind of huge advantage compared to the category of all modules, or even of all finitely generated modules. So I want again to say that U of G is a Noetherian algebra, so the category of finitely generated modules is a reasonable category, but still finitely generated U of G modules usually don't have finite lengths. So this says that category O kind of is much nicer than even nice categories of G modules. But here comes something which is not such a good thing. Category O has infinitely many simples, in fact, continuum many simples. Simple objects in category O are indexed by the so-called highest weights, which are the elements in the dual space to the Cartan. So we have infinitely many simple objects, which in particular means that category O is quite far from being something like a module category over a finite dimensional algebra. But now we go into kind of the positive side, is that category O actually splits into a direct sum of blocks of indecomposable subcategories, into a direct sum of blocks with respect to the action of the center of the universal enveloping algebra. So when we just take the splitting with respect to the action of the center, the corresponding blocks might still be decomposable. But regardless of that, each of these blocks defined by the action of the center is now equivalent to the category of finite dimensional modules over some finite dimensional associative algebra. So we started from something which is very infinite, we put some conditions, and we arrived at the object which in the representation theory of finite dimensional algebras is the main protagonist. So category O splits into blocks, and each block on its own is the category of finite dimensional modules over some finite dimensional associative algebra. Of course, the kind of the bad part of the news here is that this finite dimensional associative algebra is not very easy to write down, but there are some properties of it which can be established, and one very important property for today's talk is that all these algebras are quasi-hereditary. So each block of category O is a module category over a quasi-hereditary algebra. For this talk, I will focus only on one block. It is called the principal block and usually denoted O0. And the 0 means that this block, this is the indecomposable direct summand of O, which contains the trivial module, the module with highest weight 0. This is a one-dimensional module which is killed by the Lie algebra G. So all elements of G act on it as 0. So this is a finite dimensional module. It's a highest weight module with highest weight 0, and we have the corresponding block of O. It's called the principal block. So how can we get a feeling about the size of this block? So our algebra G has a Weil group. The Weil group, it's a group of some linear endomorphisms of the dual of the Cartan. This is the dual of the Cartan is a part where we have the root system of G, and the Weil group is just the Weil group of that root system. So for example, for SLN, the Weil group will be just the symmetric group Sn. And the point about this principal block is that the simple objects in this principal block, they are indexed by the elements in the Weil group. So these are exactly the simple highest weight modules with highest weights W dot 0, where dot is not the usual action of W H star, but the so-called dot action. It's a usual action shifted by one vector, which is the half of the sum of positive roots. So we have a module category over some finite dimensional algebra where simple objects are in bijection with elements in the while group. Okay? So since it's a module category over a finite dimensional algebra, so let me denote the basic version of this algebra by A. So this is unique up to isomorphism now, because I require it to be basic. So we have a basic finite dimensional associative algebra A, such that its module category is equivalent to O0. And since it's a module category or finite dimensional algebra, it has projectives, enough projectives and enough injectives. So each simple has an indecomposable projective cover, which I denote by PW, and it has an indecomposable injective envelope, which I denote by IW. Okay? And as I already mentioned, one of the main results of Bernstein-Gelfand in their original paper on category O is that the algebra A is quasi-hereditary, and the quasi-hereditary algebra requires as part of the structure the collection of standard modules, and these standard modules are exactly the Verma modules. Here is how Verma modules look like. We take a one-dimensional module over the Cartan subalgebra, extend it to n plus trivially, so n plus kills it, and then we freely induce to the rest of G. So this is the Verma module with highest weight lambda. I will denote it by delta lambda, and in the principal block, delta W is just delta with highest weight W dot 0. And in the quasi-hereditary structure, we also have the costandard modules, these are nablas. And we also have in the quasi-hereditary structure the tilting modules. So these are modules which have both filtration with Verma quotients or with standard quotients and the filtration with costandard quotients. Okay. Category O also has a simple preserving duality. This is a contravariant equivalence, involutive equivalence, which preserves isomorphism classes of simple modules. And so using this duality, in particular, costandard modules are duals of standard modules and tilting modules are self-duals. Okay, so the first natural question, if one talks about homological invariants of some algebra, is to, let's say, determine projective dimension of some classes of modules. First of all, since we already know that our algebra is quasi-hereditary, any finite dimensional quasi-hereditary algebra has finite global dimension. So we know that, our principal block O0 has finite global dimension. And one can also say that when we speak about quasi-hereditary algebras, a part of the structure is an order on the set of isomorphism classes of simple modules. So we know that our isomorphism classes of simple modules are in bijection with elements of W, and then the corresponding order, which defines a quasi-hereditary structure, will be the Brugha order on W. So in particular, with respect to this, we have the length function. So in W, we have simple reflections, and any element can be written as a product of simple reflections, and the minimal such, the number of factors in the minimal such product is called the length. So we have the length function. And we have the unique longest element, which is usually denoted by W0. In the symmetric group, this is a transposition when you write 1 to n in the reversed order. And in particular, the length of this element is the number of positive roots in our root system. Okay, so why is it relevant? Because in the same original paper of Bernstein, Gelfand in 75, they show that the global dimension of the whole category O, in particular of this principal block O0, is bounded by 2 times the length of W0. Basically, it's bounded by the number of roots of our Lie algebra. Okay, and here is a precise result for structural modules. Of course, it's not very interesting to study projective dimension for projective modules, but for all other structural modules, injective, simples, tilting, standard, and costandard, it's an interesting question. So here is the theorem. It's the first part of the theorem. There will be the second part much later. So this is a part about easy projective dimensions. I don't know, I mean, many people knew this for a very long time. And one part, like estimate in one direction, as I will mention on the next slide, can be done fairly easily, follows from the arguments in the original BGG paper. Okay, so the projective dimension of the standard module delta W is just the length of W. So it's given immediately in terms of this combinatorics of the Coxeter group W. The projective dimension of nabla W is a bit more complicated as a formula, but the terms are the same. So we take 2LW0 minus L of W. And the projective dimension of LW is the same as the projective dimension of nabla W. So that's the first statement. And I will explain how you prove it a little bit. So the easy direction of the proof. Yep.
Can I have a naive question? Is the O0 can be considered as a full abelian subcategory of O, of the category O?
You mean O0?
Yes. O0
Yes,
is the full abelian subcategory of the category O, yes?
Absolutely. It's a direct summand. It's an indecomposable direct summand of category O as a category.
Okay.
Yeah. O0 is a full abelian subcategory, and it has a complement in category O, actually. Yeah.
Do we can think about the notion of tau, for instance, in O0? Something like Auslander.
I mean, it's a finite. O0 is equivalent to the category of modules over a finite dimensional algebra. So whatever you can say about the finite dimensional algebra, whatever you can define for a finite dimensional algebra, you can define in O0 as well, because it's just one example.
Yes. Okay. Thank you very much. Thank you.
Okay. So the easy direction of the proof, so if you want to prove something like that, you need to prove estimates in both directions. And the easy direction of the proof is the following. So there is a general result for quasi-hereditary algebras. If you have a quasi-hereditary algebra with n simple modules, then the global dimension of the algebra is at most 2n minus 2. And there is a standard proof. You can find it more or less in any book on or any overview paper on quasi-hereditary algebras. So you have the linear order, which gives you a quasi-hereditary structure, and you do induction with respect to this order and show, using the axiom of quasi-hereditary structure algebras, that the projective dimension of each delta I is at most n minus I. So the projective dimension of delta n is 0 because delta n is projective, and then it can grow only by 1 on each step. And then you do, this gives you an induction from n to 1 for deltas, and then you go in the opposite direction, but now for simples, and you prove that the projective dimension of simple is at most 2n minus 1 minus n minus I. So here it's at most n minus 1, and then it grows by 1 on each step on the induction. Exactly the same argument works if you just walk along the Brugha order. And if you do this, you will get in the previous formulas that the left-hand side is less than or equal to the right-hand side. So this is just the standard thing, which is just the same for all quasi-hereditary algebras. The question is how to prove the actual equalities. And this is tricky because then you have to basically produce this extension of the maximal possible homological degree. And in order to do this, one of the convenient ways is to see that category O is equipped with a lot of extra structure which comes from its Lie theoretic nature. In particular, it has several very nice functorial actions which are of Lie theoretic nature. So the first such action is the action of projective functors. The universal enveloping algebra of a Lie algebra, it's a Hopf algebra. So in particular, you can tensor two modules over the ground field, and you get a new module. So you can tensoring with a fixed module gives you an endofunctor of your category, more or less, or at least of the category of all modules. If you tensor with finite dimensional modules, this gives you the endofunctor of O. And projective functors are exactly the additive closure in the sense of the category of functors which are given by tensoring with finite dimensional G modules. So projective functors operating on the principal block of category O, they form a bicategory or monoidal category, which has several aliases. So it's a monoidal category of projective functors, monoidal category of Zergel bimodules, or sometimes it's called the Hecke category or the Hecke bicategory, the Hecke monoidal category. Why, especially why the word Hecke appears here, will be explained a little bit later in the talk. So this is one kind of functorial action category, or we can act by projective functors. Another type of functorial action is the action of the so-called twisting functors. And they are defined using localizations of U of G. U of G is an infinite dimensional algebra. And if you pick wisely elements in U of G, you can localize them, so invert them. And you can use this localization to define some endofunctors of module categories. And in fact, using the twisting functors, you can show that derived twisting functors, when acting on the boundary derived category of O0, they give an action of the Artin braid group on that category. So they satisfy the relations in the Artin braid group. And the corresponding bicategory or monoidal category or whatever which they generate, or two category, that's exactly the two braid group in the sense of Rukia. So the action on OY twisting functors gives you one of possible interpretations of Rukia's two braid group. Okay, and here is the technical slide. It's not about reading the details. This is just copy-pasted from the paper. How you prove that some dimension of something exists, and you usually prove it by induction. So we want to prove that the projective dimension of delta is exactly LW. So here, so you need to produce an X of degree LW from delta to something, and you produce this X to the trivial module. And you do it by induction on W, with the case W is equal to E being trivial. And to do the induction step, what you usually do, you go to the derived category, and then in the derived category, you use properties of your twisting functors, because for them you can compute how they act on Verma modules, on simple modules, and so on. And by applying these twisting functors, they are self-equivalences, moving them around, you simply reduce your original question to the question when the length of the element is shorter. And this gives you the induction step. So on the paper, this looks like a kind of a short element, but there are many things into here which are properties of certain functorial actions which act on your category. So there is some heavy machinery involved here, but at the end, it is summed up in a short and concise computation. But this is a typical example how you prove that something, that some extension really exists in category O. Okay. So now I said, I already mentioned the name Hecke category. So why is that name? Because there is some combinatorics of the Hecke algebra which is important for understanding category O. So what is the Hecke algebra? The while group of G, so the group W of G, it's a Coxeter group with respect to simple reflections. When we choose triangular decomposition of G, we chose the set of simple, the set of positive roots, alternatively the set of simple roots. So we chose simple reflections. And we have the Coxeter presentation of W with respect to those reflections. And this Coxeter presentation consists of the braid relations plus the relations that the simple reflections are reflections. They square to the identity, the involutions. So what is the Hecke algebra? The Hecke algebra is a deformation of W, of the algebra of W, where you take the same generators, well, you just denote them by a different symbol. You keep the braid relations are just kept as they are. But instead of the relation for the involution, so the relation for the involution says that the eigenvalues of S are plus and minus 1. So S is diagonalizable with eigenvalues plus and minus 1. So instead of this relation, you write the relations that your new generator HS is diagonalizable with eigenvalues V and minus V and V inverse, where V is something, some parameter, and this means that your Hecke algebra is actually an algebra over the ring of Laurent polynomials in this new parameter V. So as an algebra over this commutative ring, the Hecke algebra has the standard basis, which is indexed by elements of W. So you take a W reduced expression and you multiply the standard generators along that reduced expression. But it also has another basis, which is called the Kazhdan-Lustig basis. So this one is defined in terms of some self-dual properties. So it turns out that the Hecke algebra has a nice involution, and you can use the self-dual objects for that involution together with some recursion to define a new basis in the Hecke algebra, which is called Kazhdan-Lustig basis. So we have two different bases, and we have the transformation matrix from one to the other. So entries of that transformation matrix are known as Kazhdan-Lustig polynomials. So Kazhdan-Lustig polynomials are exactly the entries of the transformation matrix from the standard basis to the Kazhdan-Lustig basis, or back. And these polynomials have some remarkable properties, in particular, remarkable positivity properties. So first of all, they are elements by definition of this ring of Laurent polynomials in V and V inverse. And it turns out that they all have non-negative coefficients. And actually, they are really polynomials, not Laurent polynomials. Moreover, if you take the structure constants of the Hecke algebra with respect to the new basis, so these structure constants are now Laurent polynomials, but it turns out that they also have non-negative coefficients. So there are some non-negativity phenomena which here are kind of very interesting. Okay, and what is the relation to category O? So we can specialize the Hecke algebra to the group algebra of the original Coxeter group by, let's say, inducing scalars to the complex numbers and then setting these equal to 1. And then just, so if v is equal to 1, then this relation becomes this relation. This is somehow clear. Okay? So in particular, we can take the Kazhdan-Lustig basis for the Hecke algebra and form the corresponding Kazhdan-Lustig basis in the integral group algebra of the Weil group. So I will need this object in order to define the next statement. Okay, so let P be the bicategory of projective functors which acts on the category O. So I remind you that projective functors are direct summands of the functors of tensoring with a finite dimensional G module. Okay, there is a theorem by Bernstein and Guilfin Jr. from 1980, which actually determines the indecomposable objects in this bicategory P. It turns out that indecomposable projective endofunctors of O0 are also in bijection with elements of W. So if for element W in W we denote the corresponding indecomposable projective functor by theta W, it is uniquely identified by the property that it sends the dominant projective module, the projective module for the identity, to the projective module PW. And this we can now use to formulate the following theorem, which is implicit more or less in the work of Bernstein and Guilfin in 1980, but then explicit in the work of Zörgel. So if we take the split Grothendieck group for the action of this additive category of projective functors, on the, so for the additive category of projective functors, we take the split Grothendieck group, and O0 is an abelian category, we take the usual Grothendieck group. So this gives us the right regular representation of the integral group algebra of the Weil group. So both of them give us the integral group algebra of the Weil group, and the action is just the right regular action. So the only problem is what kind of basis do we have? And the standard basis of ZW corresponds to Verma modules in the category O0. And this basis of indecomposable projective functors, alternatively the basis of projective indecomposable projectives in O0, it corresponds to the Kazhdan-Lustig basis in the corresponding split Grothendieck group or the Grothendieck group of O0. So this shows you the relevance of the Hecke algebra and the Kazhdan-Lustig combinatorics here. Okay, and this was called the ungraded categorification, and kind of ungraded corresponds that you don't see the Hecke algebra, we specialize it to V is equal to 1, we only use it to define the Kazhdan-Lustig basis here. But otherwise, we don't see V. V disappears from this picture. So how to get V back? Getting V back means graded categorification. There is a theorem by Zörgel from 91, which says that the algebra A behind the regular block of, principal block of O is COSUL. In particular, it's positively graded. So we can consider the category of finitely generated graded modules over this algebra. And this is the category which is usually called the graded lift of the principal block of O0. Of course, we have a functor from graded modules to ungraded modules. We just forget the grading. And all structural modules are in the image of that functor. So they all have graded lifts. And for indecomposable modules, there is a standard thing that graded lift is unique up to isomorphism and shift of grading. And also, even the indecomposable projective functors admit graded lifts. Again, unique up to isomorphism and shift of gradient. So we have the category of graded projective functors acting on the category of finitely generated graded A modules. And the graded categorification statement, which is due to Zörgel, is that now if we take the Grothendieck group of the category of graded modules and the split Grothendieck group for the category of graded projective functors, which acts here, then what we will get is the right regular module over the Hecke algebra. So the Hecke algebra enters the picture as the graded version of the categorification. And our variable v in the definition of the Hecke algebra in the story gets interpreted as the shift of gradient. So we have Laurent polynomials in v, and multiplication with v means just shift of gradient. Okay, so now I can discuss the remaining projective dimensions, and you will see how kind of the level of difficulty goes up here. So I need to define Lustig's A function. So this is a function which takes an element of the Weil group and gives you a non-negative integer. And it is defined using the combinatorics of Kazhdan-Lustig polynomials. So the value AW is the maximal degree of the structure constant when you freely choose the left-hand side. So we have, so I use here Einstein notation. So this is a sum over all W. If you take two coefficients, two elements in the Kazhdan-Lustig basis, hx underlined and hy underlined, you multiply them, you will get a sum over W of such expressions. So you have the structure constant hwxy as assigned to each hw underlined. Now, if you fix w and you vary x and y, you look at the structure constant, and it's a Laurent polynomial, which is invariant under swapping v and v inverse, and you take the maximal possible degree of that Laurent polynomial over all x and y. So here is an example of this A function for S3. So S3, it's a group with two generators S and T, and relation STS is equal to TST. So you have 6 elements, E, S, T, ST, TS, and W0. And the value of the A function on E is always 0. And then on ST, ST, and TS, it's 1. And on STS, it's 3. Yeah, so this is such a function. You see that it is defined in terms of Kazhdan-Lustig combinatorics because it needs Kazhdan-Lustig basis for definition. And here is the result, which I proved some 15 years ago. First for type A, for SLN, and then in general. The projective dimension of the tilting module TW is just equal to the value of the A function on the index. And the projective dimension of the injective module IW is 2 times the A function of W0W. So here the answers are given in terms of the Kazhdan-Lustig combinatorics, and the proofs are, I'm not going to talk about that. That is, the proofs are much more involved than for standard, costandard, and simple modules. But here at least there is a result. So one good thing about Kazhdan-Lustig combinatorics is that it gives you the full answer about the Cartan matrix of O0. So one reformulation of the fact that the algebra behind O is quasi-hereditary is that each projective has a filtration whose subquotients are Verma modules. And there is the so-called Kazhdan-Lustig conjecture formulated in the original paper of Kazhdan-Lustig, which was very soon proved. It says that the multiplicity of the graded projective delta y shifted by minus k in the standard filtration of Px is exactly the coefficient of v to the power k in the Kazhdan-Lusztig polynomial Pxy. So these multiplicities are given by the coefficients of the Kazhdan-Lusztig polynomials. And since A is quasi-hereditary with simple preserving duality, we have the BGG reciprocity, which says that the multiplicity of delta in the projective is equal to the multiplicity of simple in delta. And so if these multiplicities are given by coefficients of Kazhdan-Lusztig polynomials and these as well, and then the Cartan matrix of A is just the product of the matrix of these multiplicities and these transposed. So in other words, the entries of the Cartan matrix for A can be computed using the Kazhdan-Lusztig polynomials. So this is the relevance of their combinatorics here. As I already mentioned, Zörgel proved that the algebra A is COSUL. In particular, it was graded. And this means that the minimal graded projective resolution of simple A modules, that they are linear. So in the graded picture, we have two-dimensional picture, grading as in the graded algebra, and then the homological grading. So you have a two-dimensional picture, and causality means that heads of the parts of the projective resolutions of simple modules are aligned along some diagonal in that picture. And these resolutions, so resolutions of simple modules, are exactly the indecomposable projectives for the COSUL dual of A. It's always for any COSUL algebra A. But actually, Zörgel also proved that A is COSUL self-dual. Right? And this self-duality, it's not a very trivial thing. It induces a non-trivial map on the primitive idempotence. But in particular, it reduces determination of extensions between simple modules to the graded Cartan matrix of A. And since we know that the later is given by the Kazhdan-Lusztig combinatorics, this implies that extensions between simples can be computed using the Kazhdan-Lusztig combinatorics. Next, a little bit about the Serre functor. So A has finite global dimension. So by general reasons, the boundary derived category has a Serre functor, and the Serre functor is a derived of the Nakayama functor. And this Serre functor also has a least theoretic interpretation, which is very nice in terms of the actions which I mentioned before. So, as I said, the Artin braid group acts on DBA via derived twisting functors, which are defined using some localizations least theoretically. And also some time ago, together with Katarina Stroppel, we showed that the Serre functor on DBA is one of the functors of that action. Namely, it's a functor, it's a square of the left derived of twisting by the longest element. It's quite interesting to point out that W0 square, it's the identity in the while group, but in the braid group, it's a non-trivial central element. And in type A, it's the generator of the center. It kind of aligns nice with the properties that Serre functors compute with all autoequivalences. So this functor, it's the central object of the action of your group. Okay, from the quasi-hereditary structure, we also have Ringel self-duality. So if we take the direct sum of all tilting modules and take the endomorphism algebra, this is a definition of the Ringel dual of a quasi-hereditary algebra. And Zörgel proved that that algebra A is actually Ringel self-dual. So it's isomorphic to R of A. And similarly, as for COSUL duality, this induces a non-trivial map on primitive idempotence. But in fact, this result in terms of functorial actions is not very complicated. One can show that if you apply the left derived of the twisting for the longest element to the projective PW, you get exactly the tilting given by W0W. And this is a self-equivalence. So the endomorphism algebra of the direct sum of all projectives goes to the endomorphism algebra to the direct sum of all tiltings. This is exactly the Ringel cell duality statement. But you see, so in the Ringel cell duality, this functor appears directly, while in Kosul, while the Serre functor is a square of it. So somehow it shows that the Serre functor is a square of the Ringel duality functor in this setup, which is a nice observation. Also, which was pointed out in other setups by other people like Henning Krause, for example. And finally, I want to talk a little bit about the Auslander regularity of category O. Recall that a finite dimensional algebra is Auslander regular, provided that it has finite global dimension, which category O has. And the ice term of the minimal injective resolution of the projective generator has projective dimension at most I. Here is a recent result by Han-Kyun Ko, Raphael Mudren, and myself, which was published in 2021. The algebra behind any block of category O, in particular the principal block of category O, is Auslander regular. This is not totally trivial, but the main ingredients in the proof is all these formulas for projective dimensions of tiltings and injective modules, which I mentioned before, combined with Kosul-Ringel self-dualities and properties of the action of projective functors. So you can put everything together, and after some work, you get that the algebra behind category O is really Auslander regular. Okay, and maybe two more slides. Projective dimensions of some other modules, some natural class of modules, the so-called translated simple modules. We have everything what we need to define them. So we have the indecomposable projective functor theta W operating on O0. So it is uniquely defined by the properties that it sends a dominant projective to the projective indexed by its index. And we also had the Lustick's A function when we maximize some degree of the structure constant by varying two other guys in the definition. So now let's define the B function. Now it has two ingredients, and we maximize the structure constant by fixing the two ingredients of the B function and varying the third ingredient in the structure constant. So it's a very natural generalization of Lustick's A function. This one has two parameters. It's much more complicated than Lustick's A function, but it can be used to prove the following. So it's again...
There is one question in the chat, maybe. It's asked that is the category O extension closed in G mode?
No, absolutely not. I mean, it's not extension closed for the reason that one of the requirements is that the modules in category O are H diagonalizable. So in G mod, you can extend modules and kind of get something where H acts locally finitely, but no longer diagonalizably. So it's not extension closed in G mod. It's not even X1 closed in G mod. Yeah. But it's a good question. In order to have something extension closed, there is something which is called thick category O, where you allow H to act locally finitely, and then that thing will be extension closed in G mod. Yeah. I can give, who is interested, I can give a reference for the later result where this is discussed. Okay, so the final result is about the projective dimension of the module of the form you take a simple and you apply an indecomposable projective functor to the simple object. There is an explicit criterion where the outcome is non-zero, so you can describe where the outcome is non-zero in terms of the Kazhdan-Lusztig combinatorics. So for x and y, such that the outcome is non-zero, the projective dimension of this outcome is given by this expression, which is both some combination of Lustig's A function and this B function. And again, the proof of this is much, much more complicated than the proof where only the A function is involved. Okay, so this is kind of the description of various results about homological properties. And I think on my last slide, I listed some open questions. So some open questions about category O. First of all, problem one, very classical problem, describe extensions between standard modules. Extensions between simple modules can be computed using Kazhdan-Lusztig combinatorics. For standard modules completely open, there is one recent paper where some alternating sums of extensions are described in terms of R polynomials, but in general, it's a very open question. So we have twisted functors acting on category O. You can apply them to projective modules, produce what is called twisted projective modules. So all these, they form some tilting, generalized tilting modules in category O, and projective dimension of them is known only in some special cases. Very interesting question. And you can say the same thing about applying twisting functors to these quasi-hereditary tilting modules. So you have, using this braid group action by twisting functors, you can define various classes of generalized tilting modules in category O, and one can ask the question with respect to which of those classes of generalized tilting modules category O is analog of Auslander regular. Also, this is known only in some cases, and the answer seems to be quite non-trivial. And another, so now it sounds as a very innocent problem, but seems very hard. There is a conjecture that in type A, the modules which I talked on the previous slide, if you start from a simple and apply the indecomposable projective functor, this is either zero or indecomposable. If this is true, this would simplify many things. There are many things now which kind of use this as an input. So it's also an interesting open question. Okay, so here's a list of references. Actually, I have a series of six papers which I started myself and then continued with several co-authors with Kevin Coulombier, Han-Kyun Ko, and Raphael Mgen. All are called some homological properties of category O, and then you have 1, 2, 3, 4, 5, and 6. And the results which I described today in the talk, most of them can be found in these papers, so you're welcome to take a look if you are interested. So thank you very much. Yeah.
Thank you very much for your nice lecture. So, are there any questions? You can unmute yourself and ask your question directly, or you can write it in the chat box. Just to start.
Yes, thank you. Can I ask a question?
Yes,
sure.
Yes, thank you. I think in the previous slides, you have some formula on the projective dimension of simple modules. On LW, you have a, I think you have a formula saying that there's the double of length W0 minus length of W.
Yeah.
I mean, in that case,
it's somewhere very, yeah. It's somewhere long time.
Yes, yes. I mean, do you mean that in this case you can calculate exactly the global dimension of A?
Oh, but the global dimension of A is just 2 times L of W0. This is this is easy.
Easy. Okay. So that's
Yes,
because
I mean,
you just say that this is inequality, but you say they are really equal.
yeah. So the global dimension of A is the algebra behind the principal block of O. The global dimension of A, the bound that it's bounded by 2 times L of W0, this is a theorem in the original paper of Bernstein, Gelfand. And then they have the remark, the last remark of the paper, which basically says that one can show that the X from the trivial module to the trivial module of degree 2 LW0 is non-zero. This is not an obvious question, and they don't say how you show it, but they say that one can show, and the claim is true. Already BGG knew that this is the exact value because they produce a module who has a self-extension of that degree. But this is because they, I mean, in reality, this means that they understood the algebra, the role coinvariant algebra played in the whole thing, because the X algebra of the trivial module in category O, it is the coinvariant algebra of the Weil group, which is graded such that simple reflection has degree 2. So the extreme X has degree exactly 2 times length of W0.
Okay, so in that case, the global dimension is yes, you know.
Yeah.
Okay, thank you, because you don't mention this equality. Thank you very much.
Yeah. Thank you.
Is there any other question?
I have a question, Java.
Yes, please.
Thank you for your very nice talk. My question is that it seems that there is some connection between the cluster structure on Lie algebra and this category. Is there some connection between the categorification of the corresponding cluster algebra and this category of O?
I don't know. I don't know the answer to this. I don't know of any connection between any cluster structure of category and category O, but I don't claim that it doesn't exist. Maybe it exists, but I simply don't know about it. Sorry.
Oh, thank you.
Other questions? So
Sorry, another question.
Yeah.
You mentioned that this in this case the functor is a square of that thing. Do you think this is some kind of more general phenomenon? I mean, this.
If I remember correctly, Henning Krause has a paper where he proves something very similar for some Schur algebras or in some other setups.
Okay.
So here the functor is a square of the Ringel duality factor, and I think there are similar results in other setups.
Yes. Okay. Thank you.
Walter, there is a question in the chat box. Can you see it, or I can read the last question?
Yeah. Is there a characterization of the abelian what?
Maybe axiomatization.
For example, the module category of every Auslander regular algebra satisfying some condition. No. There are many examples of Auslander regular algebras which are very, very, very different from O. No, this I don't believe at all. I mean, for Auslander regular algebras, one should look at examples produced by René Marcinczyk and Osamu Iyama and some others. So there are many examples which look as completely detached from category O. So it's just category O is just one of examples. And probably it's somehow related to the fact that the universal developing algebra is Auslander regular.
So
May, may I ask a question as well?
Yes, please go ahead.
So, if I understood correctly, there is an equivalence of excuse me. If I understood correctly, there is an equivalence of categories between between modules belonging to some block and modules of some finite dimensional algebra A. And if I remember correctly, this algebra A is an endomorphism algebra of some projective generators. Could you be more precise in this equivalence? In this, I mean, explicitly, could you describe this equivalence of categories? Probably it is a standard. This question has a standard answer, but I don't know this answer.
Yeah, I'm not sure I understand the question. I mean, abstractly, you can describe it explicitly. You just take the direct sum of indecomposable projectives in your block and take its endomorphism algebra. But concretely, I mean, if your question is whether it's easy to define an algebra behind category O by generators and relations, like by quiver and relations, the answer is this is not very easy. You can use, so there is an approach, you can use Khovanov-Lauder algebras to define an algebra which is not basic. So the main point which is not basic, which is whose centralizer subalgebra, the centralizer of some idempotent, fairly explicit idempotent, is equivalent to the block of O. So you have to give up basic, and you have to kind of only allow kind of the algebra and an explicit idempotent, and you take the centralizer. In these terms, you can describe the category O by some kind of generators and relations.
Okay. Thank you very much.
So, are there more questions, comments? It seems that it's not the case. So let's thank Walter once more. Thank you very much.
Thank you. Thank you.
Oh, it seems that there's one question by Ramin. Oh, no, it's not. Okay. Thank you very much. And
Thank you. Thank you.
have a
Bye-bye.
nice day. Bye.
You too.